recording for the virtual students for this class. We are looking at number 20. What page did I say it was? 705. So page 705, number 20. Somebody in the back, Mr. Rhodes, can you read off that problem aloud for us, please?
You can sometimes see an eagle gliding with its wings flexed in a characteristic double V shape. Each wing can be modeled as two right triangles as shown in the figure. Find the measure of the angle in the middle of the wing, angle DHG to the nearest degree.
Okay, so I'm recreating the picture of the wings of an eagle. We know that this is 49. This is H. We actually also know that this is 32. It's actually written out here to the left, but we know that the height is 32. We have a right angle here. This is E. And then it has G, like over here. Right? And so then the way that the problem is written or questioned is finding the measure of two angles. So I'm going to call this angle 1, and I'm going to call that angle 2. Does that make sense, Mason? Okay, so really what happens then is I'm trying to find the measure of 1 and 2 and add them together. And that's a right angle as well. Okay, so let's take a look at the measure of angle 1 first. I'm going to shade it in so you know which exactly angle I'm talking about. This one right here. Okay, so that's the angle we're talking about. And so then I have to, if you remember, I talked about this 2 days ago. You got to have an inner dialogue going on in your head as you determine the sides so we can figure out which trig function to use. We only had 3 trig functions to choose from. Sine, cosine, tangent. SOHCAHTOA. Okay, sine, cosine, tangent. All right, so if I'm dealing with angle 1 here, which I am, I'm pointing at it in the picture, side 32, the length of 32, that would be considered adjacent to angle 1. This is the inner dialogue. I'm writing it down so you guys can see it. But this is something you can just do right in your head. Okay? Side 49 would be the hypotenuse, because it's opposite the right angle. Okay? And so then I think, all right, which sine function uses an A and an H, or the adjacent and the hypotenuse? Cosine. So I know that the cosine is adjacent over hypotenuse. So now I'm going to create an equation. The cosine of angle 1 is equal to 32 over 49. Anytime I go to find the measure of an angle, I'm going to use the inverse function. Okay? So the inverse function, cosine, that looks like this. Get your calculators out. You can use it on your phone. You can use the calculator. Clear, clear, clear. Inverse cosine, 32 over 49 equals, and we have 49.2. So the measure of angle 1 is approximately equal to 49.2. 49.2. Everyone good? We're halfway. Okay, let's go to the next one then. So now we're going to find, I'll color it in with a different color. Now we're going to find the measure of angle 2. Okay, so the measure of angle 2, when I look at this carefully, I know that the length here given, this is given in the problem, is 38, and this is 43. Opposite angle 2, that means 38 is the opposite side, and 43 is the hypotenuse. I'm going a little bit faster. Which trig function uses opposite and hypotenuse? That is the sine function. Hypotenuse. The sine function. So, clear that over here. The sine of angle 2 is equal to the opposite over the hypotenuse, so katoa. Use the inverse function again. Inverse of sine 38 over 43. Calculator, clear, clear, clear. Inverse sine 38 over 43. And we get 62.1. So the measure of angle 2 is 62.1. That's not our answer because we realize we have to add these two together. 1 plus 2 gives us 111.3, and that's the measure of angle DHG. 111.3. Any questions on number 20? That make sense? Got it? Okay. If you haven't submitted that assignment, make sure you get submitted today. All right, so that was page 705. Yes?
I have a question on 23, though.
Yeah.
So it says, use midpoint, whatever. All I did was I did the opposite over adjacent, which tangent, and
You can do that.
I got the answer.
Yep, you can do that. Mm-hmm. It doesn't want you to because that was in section sine and cosine. It wants you to do a double one,
Yeah.
but tangent works. Nope. When it comes time for a quiz, for sure. Good. Other questions? Okay, notes out. Let's take a look at section 13.3. These are called special right triangles. Okay, if it's important enough for me to write it down, you probably should write it down. Special right triangles. There are actually two types. There is a 45, 45, 90 right triangle, and there is a 30, 60, 90 right triangle. We're only going to concern ourselves today with the 45, 45, 90. We're going to do the 30, 60, 90 on Monday. Okay? So this is what we're going to look at. So let's create a right triangle that's an isosceles triangle. So there's a right triangle. Did you guys hear that term? Isosceles? Isosceles triangle, that means two sides are the same length. Scalene means all the sides are different lengths. By the way, have I talked to you about the definition or the scenario of, not really definition, the scenario of two lines which never intersect but are not parallel?
No.
Let me say that again. Two lines which never intersect but are not parallel. Can you guys envision it? Two lines that never intersect but are not parallel. Anybody?
A circle.
Two
Three
lines.
circles.
No. Two lines. Two lines that never intersect but are not parallel. It is. Okay, let me help you out. All right, you got to use your imagination a little bit. Here we go. Take a look up here. Think of a line that goes from here in between these two rows all the way to the back wall. So everybody see that straight line? Got it? Now, think of a line that's over here that's vertical. It goes straight up and down. You see that?
Never touch because.
Those lines will never touch, but are they considered parallel? They're not.
Or the line could be tilted even.
That's right, and go underneath it. Right, yeah. But you get the idea. That's just one sample. There's an infinite amount. But they have a special, so a line there, and a line going straight up and down.
What was your question?
Those are considered skew lines. That's the terms. SKEW. Which means they never intersect, but they're not parallel. Now, there's a little bit of a trick in there because they're not in the same plane. It's three-dimensional. If you think about it, You couldn't have a single plane that went through this line and this line. It would have to twist. The reason why I'm bringing up three-dimensional figures is because of what we're talking about. Austin, you all right back there?
Yes,
All right, so the reason why we're talking about three dimensionals, why I'm bringing this up, is because of what we're talking about here is the basis for three-dimensional figures in the future. Watch this. If I have this picture, does anybody know what this is called? Not yet, not yet. Don't answer. What's that called? Pyramid. That's a three-dimensional isosceles triangle with a square as a base. This is the last section that we deal with here in geometry in April and May. Okay, and so what we're doing right now is prepping us for that, which honestly is great for applications in the real world. Because we start talking about cones and prisms and spheres, which are all the things that we've talked about in two-dimensional, but then we expand it to three-dimensional. Just like parallel lines and skew lines. Parallels two-dimensional, skew lines make it three-dimensional. Okay? Algebra, you do a lot more with three-dimensional parabolas and curves, things like that. All right. That being said, let's get back to the 45, 45, 90. Now let's investigate the parts. There's a lot to this. It doesn't seem like it, but there's a lot to it. Okay, so stay with me here. The legs, I'm giving you the length of the legs. We could measure it with a ruler, but I'm giving you the measure of the legs. And we're saying they're 3 and 3. Okay? Use the Pythagorean theorem at your seat and go ahead and solve and find the length of x. I'll say it again. Use the Pythagorean theorem at your seat and find the length of x. Okay, so 9 plus 9 is equal to x squared. 18 is equal to x squared. How do we solve for x when it's x squared? What do we got to do? Take the square root. Whatever I do to one side,
You gotta do the other.
I have to do the other. So then we have x over here. What's the square root of 18?
4.24.
Okay, what if we said no decimals?
Oh.
You got to factor it. Square root of 9 times the square root of 2. We end up with
I can't do that.
3 radical 2. Okay? Now, the reason why that's important is because it gives us a shortcut. We all like shortcuts. You know, the shortcut is to find the lengths of the sides. If this is an isosceles triangle, if this is 3 and that is 3, well, then we know that this is 45 and this is 45. Has to be. Because the sides are the same, and then so are the base angles. Sides are the same, and so are the base angles. Does that make sense? Okay, so then there's a shortcut. If I know that the length of the leg is 3, what do I need to multiply to get to the hypotenuse? Leg to hypotenuse. I multiply by the square root of 3. And I do show that right there. What about going from the hypotenuse to the leg?
Where is 3?
divide, not the square root of 3, I'm sorry, the square root of 2. I divide by the square root of 2. Right there. Okay? All right. So take a look over here at this poster. Had this poster up all year because it is something you don't have to memorize, but you need to know how to use. Okay, not this one by Jimmy that we looked at the other day, but this one right here. Okay? So it's going to stay up there. So you don't have to memorize these rules, but you got to know what it means. All right? So if I look at it carefully, today we're just going to look at 45, 45, 90. All right? So I have 45, 45, 90. What's the length of the side on that poster? A, or it's a variable, like X. Okay? Well, in other words, what that means is it doesn't matter what this length is. It can be any length. It could be like we have here, 3. It could be any length. That makes sense? Okay, now, to go from a leg, I wish this poster had this, but it doesn't. If I would draw an arrow, like an arc, an arrow, from the leg to the hypotenuse, what's the difference? We just multiply by what? Square root of 2. So that's what I wanted to show you here. When I'm going from a leg, this is the shortcut. When I'm going from the leg to the hypotenuse, I multiply by the square root of 2. This is a rule. It is always true. You can memorize it. You don't have to. You can. But it's always true. It does not matter if this one was 3 and 3, right? What if these were 5 and 5? Would it change the rule? No. What if it were 12 and 12? No. Does not change the rule. So if it were 12 and 12, it would be 12 times radical 2. So this would be 12 radical 2. You see, that does not matter what the length of the leg is. It's a rule. You multiply it by square root of 2. What if you're going the other direction, though? What if they give you the hypotenuse and you're going to the leg? What do? You divide. Opposite. So you should be able to tell from that, from this picture, if I go from this to here, I'm going to divide by the square root of 2. That's the rule. It always works. Okay? There's one other thing I want to investigate with the 45, 45, 90, and then we're going to look at an example. Okay, so now, keep this in mind. What if we start looking at, like we have in the past, the trig function? Okay, so get your calculator out and go ahead and tell me what the sine of 45 degrees is. I don't care, somebody, doesn't matter. Everyone's going to get the same answer. What is it? 0.7. Keep going.
0.7.
Yeah, let's just go out to 3. Okay, just so that we all see. Everyone should see you get 0.707. Okay, go ahead and do the cosine of 45. Should get the same thing. Everyone see that? Okay, so, well, those are complementary angles. Remember that if you add up to 90 degrees, they should be the same? We did that the other day. Okay, so 0.707. Well, what if we don't like the decimals? Watch this, okay? What if I go the sine of 45, and this picture here is equal to the opposite, which is 3 over 3 radical 2. Right? The opposite, 3 over 3 radical 2. Opposite over hypotenuse, sine. Everyone okay with that? Okay, so in your calculator, go ahead and simplify that. With your calculator, what do you get?
1.5.
You should get the exact same thing. So redo it. Make sure you got everything right with parentheses. There it is. Gotta be careful. You gotta use the parentheses properly, but you should get 0.707. Should get the same answer. Okay? I'm actually going to simplify the radical. I know we don't have a lot of practice with this, but I want to show you. If I have 3 over 3 radical 2, that's not simplified because there's a radical in the denominator. The 3's would cancel. I'd have 1 over radical 2, multiplied by the square root of 2 over 2, and I have the square root of 2 over the square root of 4, which is the square root of 2 over 2. Square root of 2 over 2 is not 1. What is the square root of 2 over 2? Let's look at it. The square root of 2. Oh, I don't want the answer clear. The square root of 2 divided by 2. Look at that. Same decimal. 0.707. If you look back at that poster, it's kind of hard to see it, at least it is for my eyes from here, but underneath the 45, you'll see that it says the square root of 2 over 2 and the square root of 2 over 2. That's the value of the sine and cosine. Yeah. The square root of 1/2, yes. Not just 1/2. Okay. All right. Questions there? All right, turn to page 712 in your book, number 6, and see if you can solve for the two lengths. Page 712, number 6, see if you can solve for the two lengths. Okay, so the first one should be pretty obvious. If this is 45 and this is 45, that means these sides are the same. So QR, everyone should get that one. That should be 2 radical 6. Because it's an isosceles triangle. Okay, now the next one, not so obvious. To go from a leg, the shortcut, to the hypotenuse, we take 2 radical 6 and we multiply it by radical 2. Now let's simplify. Radical 6 times radical 2 is radical 12. The 2 stays out in front. That's not simplified. And let's just say they tell us no decimals allowed. So we have to simplify square root of 12. It's like the old factor tree. Square root of 4, square root of 3. 2 radical 3. Don't forget the 2 out in front. And so we end up with 4 radical 3. Did anybody get the correct answer? 4 radical 3. Not the decimal. Did anybody get 4 radical 3? Okay, so we need to take some time and talk about how to simplify radicals. It's not going to go away. It's going to come back to us. All right, is everyone okay with this? Because we're done with the shortcut and everything with 45 minutes. Everyone okay? All right, you need kind of a new space now for your notes. Everyone needs to write this down. You're not going to learn it if you just watch. You got to write it down. All right, simplifying radicals. This isn't just in one section. This is math in general. You're going to use this next year and the year after. Simplifying radicals. Okay, number 1. No perfect roots allowed. Okay? Now, again, let me clarify. When we say simplifying, it's no different than if I have the fraction 5 over 10. If I have the fraction 5 over 10, that should make your skin crawl. Because it's not simplified. 5 over 10 is 1 over 2. All of you, mentally, easily, you can do that. Should be able to do that. Okay? So all I'm talking about is simplifying, but now with radicals. So it's this idea, but now with radicals. Does it mean that it's wrong? No, it does not mean it's wrong. Does it mean that it's right? No, it's not right either. Like if you had this as an answer, every math teacher you've ever had will probably count that wrong. Not completely wrong, probably give you partial credit. Right?
Half credit.
Yeah, maybe. Or -1.
5 over 10.
Right. Right? You might get 1 off or something like that. Okay, same concept. If they want you to simplify, you got to know how to simplify. All right, so here we go. The rule number 2. Now we're going to do some examples, but rule number 2. No. Now I use the word radical, but we just mean square root for now. But in the future, it'll mean cube root to the 4th root. It'll mean any root. No radical in the denominator. Denominator just means in the bottom of a fraction. That's the second one. If you have a radical in the bottom of a fraction, it's not simplified. Number 3. No fractions under radical. No fractions under the radical. All right, so now there's 3 scenarios. I'm going to give you samples of all 3. Okay? Here's a sample of number 1. The square root of 25. Don't tell me that that's an answer, because that's not simplified. Here's another sample of the first one. The square root of 18. Now, is 18 a perfect root? No, but is there a factor of 18 that's a perfect root?
Yes.
9. And so that's not simplified. That makes sense? Okay, I'm going to give you another one. What about the square root of 75? Is that a perfect root?
No.
No. Is there a factor of 75 that's a perfect root? Yeah, 25.
25.
So in order to do the first rule type correctly, you have to remember all the perfect roots. Remember that day we went through those mentally, did them out loud? That's what they all are. We went all the way up to 20. Yes.
So would 75 be 5?
Radical
times the
3.
Radical 3.
Radical 3. Yeah.
That's pretty familiar.
Yep. 5 radical 3. Okay? All right, so 25 we know is 5. Square root of 18 would be the square root of 9 times the square root of 2. We do it just like you did in 5th grade with trees. What's the square root of 9? 3. What's the square root of 2? Some decimal. We don't want the decimal, so we're going to keep it as a square root of 2. So that's simplified. 75, Bo already did it. Square root of 25 times the square root of 3. What's the square root of 25? 5. Square root of 3, some decimals. We don't want it.
We'll leave this 3.
We're going to leave it at square root of 3. Yes.
What if it doesn't have a perfect factor?
Okay, yeah. Like the square root of 17. Is that a perfect square? No. Is there a factor of it that has a perfect square? No. So then you just leave it. Square root of 17. That's it. It's a good question. All right, any questions on the first type? Get the idea? They take a lot of practice, and we're actually not going to do that much practice. They actually take a lot of practice to figure them out. A lot. All right, so let's go to the type number 2. No radical in the denominator. What does that look like? That looks like something like this. There is an example, 3 over radical 5, that is not simplified. And so there's a method to simplify that. Here's how you do it. It is called it's a big word, rationalizing the denominator. So if you ever look on YouTube and looking for videos, that's the phrase. It's called rationalizing the denominator. What it means is we have to eliminate the radical sign in the denominator. Okay, now I'm going to tell you how to do it, and then I'm going to go back and show you why it works. Okay, how you do it is you take the radical sign term and you multiply it by the numerator and the denominator. What is the square root of 5 over square root of 5? It's 1. Can I multiply a number by 1 at any time and not change the organic part of the number? Yeah, I can multiply by 1 at any time. Okay, so now when I multiply by square root of 5 over square root of 5, 3 times square root of 5 is not 15. Don't make that mistake. 3 is not underneath the radical, so that's just 3. Square root of 5 is some decimal, so we're just going to keep that as square root of 5. What's square root of 5 times square root of 5? Now let's simplify. What's the square root of 25? Notice, voila, like magic, the radical sign disappeared in the denominator. So I have 3 radical 5 over 5.
So could you just keep, so you know, like what you're gonna have in the denominator. So let's say like, okay. So let's say like, well, I just want to be sure, okay. So let's say 6, right? 3 over radical 6. You're gonna multiply that 3 over radical 6 times 3 over radical. You know what I'm saying? And then so you're gonna have 3 radical 6 on the top, and then 6 on the bottom. And is that going to work every time?
It is, which is what I was getting ready to show you. So if I take the square root of 6, and we'll use Bo's example, and I multiply it by the square root of 6, what is that? Square root of 36. What's the square root of 36? It always works. The square root of a number times the square root of the same number is that number without the square root sign. The square root of 8 times the square root of 8 is 8. Always, always, always. That's why it works. Let's do another one. Let's say that I have 2 over the square root of 3. I multiply both top and bottom by the square root of 3. 2 over square root of 3 over 3. It always works. Yes?
Okay, so can you take like the 2 radical 3 over 3 and take it multiplied by 2 radical 3 over 3 to get like a whole number?
You can, okay, yeah. So, but you're getting a different value now. Now you're eliminating the radical sign. Here's what he said. Can I multiply this by this, the same number? You are, but you're changing the problem. Because does this have a value of 1? You see what I mean? You're eliminating the radical, which is true, but you're changing the problem because you're multiplying by a value other than 1. Does that make sense? So like if I were trying to simplify something, that doesn't really simplify it. All that does is get rid of the radical. Okay? It's not a bad idea. And in fact, in the future, when you're solving for x, you actually have to do that. That's second semester. Okay. All right, good. Let's move on. Now, the third type of example. No fractions under the radical. No fractions under the radical. What does that mean? That means something like this. The square root of 5/6. That is not simplified. The square root of 5/6 is not simplified. It's a decimal, but it's not simplified. What we have to do when we have the square root of 5/6 is we have to separate it. The square root of 5 over the square root of 6 and make it into two separate radical problems. Now, that's not simplified because we have a radical in the denominator. So it was this that 3 rule wasn't satisfied. Now the second rule is not satisfied. How do we get rid of that 6 in the denominator? We just learned. Multiply by the square root of 6 over 6. Over square root of 6. Is this a value of 1? Yeah. What's the square root of 5 times square root of 6? Square root of 30. And what's the square root of 6 times square root of 6? 6. That is simplified. Square root of 30, does it have a perfect root that's a factor? Does 4 go into 30? No. Does 9 go into 30? No. Does 16 go into 30? No. So then we just leave it. It means it's simplified. We're going to give you more practice with simplifying radicals, okay? But those are the three major rules, and those are what they look like and how you simplify them. No perfect roots allowed, no radicals in the denominator, no fractions under the radical. By the way, what we just did right there is not part of the Indiana State Standards, how to simplify radicals. However, excuse me, if they don't want you to have decimals, you got to know how to do this. So they almost get to it backwards. They say, oh, you don't have to know how to. But if there are no decimals allowed, you better know how. You know what I mean? So it's a little different. Okay. Questions on those? We're going to do more. You'll get more practice with it. But they really come into play with these special right triangles. Okay, we're done. No homework for the weekend. We'll